So I will talk about an application of homogeneous dynamics to an old problem in statistical physics. It's been a long project with my long-term collaborator and friend Andreas Strömbergsson. And finally, it's come to a conclusion, and I'd like to report to you what the conclusion is. So the story starts with Maxwell and Boltzmann, who in the 1860s and 1870s pioneered the understanding that matter is really made out of small particles, and the idea that we can use the underlying dynamics of the microscopic particles to understand thermodynamics, to understand motions of clouds in the sky and so on, was quite revolutionary at the time. And we always take things for granted these days, but back then people really thought of water as just being one continuum and clouds just being in continuum. They had quite a hard time initially. Now, what I want to talk about is not the difficult problems of the Boltzmann gas. That is still a big challenge today, understanding how we can derive the nonlinear Boltzmann equation. I want to study a simpler model, which was proposed by Lorentz in 1904, 1905, to study electrons in metal. That was still pre-quantum mechanics, so we still think of classical particles moving around. The way the metal was modeled here is simply you freeze a configuration of balls, and you look at a cloud of test particles that don't interact with each other, but just with those balls, and they fly around there. And the question is, if you perform the right scaling limit, can you derive macroscopic transport equations for your particle gas? And many of you know, of course, that the Lorentz gas has served as a really fundamental model, and there are many people here who have worked on diffusion, trying to establish diffusion properties in the Lorentz gas. But I want to talk today about the original challenge that also Lorentz studied in the spirit of Maxwell and Boltzmann, which is the limit when you don't look at a fixed dynamical system, but you look at a sequence of dynamical systems. In this case, you shrink the scatterers. It's the so-called low density limit. But before I describe that, let me just fix the setup here. So P will denote the positions of the scatterer, so it'll be a point set in Rd, and we assume that it has density 1. So if we count the points in a big ball, the number of points in that big ball should be asymptotic to the volume of the ball, and let's do that for more general sets. The scatterers are just fixed open balls of radius rho, centered at the points of my set P. As I said, the particles are non-interacting, and so this means really that we're studying a one-particle dynamics, right? So you can either think of a cloud of non-interacting particles moving through your field of scatterers, or you can think of one test particle that starts with a certain random initial data. Okay, we move with constant velocity between collisions. That means just straight lines. I'm neglecting all sort of external fields. And the scattering is by specular reflection. So this just means incoming angle equals the outgoing angle of refraction. The theory that we've developed also works for a large class of potentials with compact support, but I won't dwell too much on this. They have to be spherically symmetric and compactly supported, so that the finite range here is a really important assumption. Now, because our scattering is elastic, this means that the velocity before and after the scattering is the same, so we can assume without loss of generality that the speed is 1. And that's what we'll assume in the following. Now, as I said, what we want to do is we want to perform a kinetic scaling and try to derive a limiting transport process. So what we'll do is we'll shrink the scatterers. We'll keep the point set P fixed, but we'll just take the radius of the scatterers to 0. Q and V are the microscopic phase space coordinates, and if you think of the microscopic coordinates and you shrink the scatterers, for most initial conditions you will start flying for longer and longer, right, until you hit the scatterer, because the proportion of scatterers that occupy a certain volume is going to 0. And in fact, you know, it's a classic simple argument that you can show that the mean free path length, so the mean distance between collisions, goes like 1 over the total scattering cross-section of each scatterer, and the total scattering cross-section is basically what the particle sees as it approaches, so it's the d-minus one-dimensional hypersurface through the volume ball, so it's a d-minus one-dimensional disk. So it has volume r to the d-minus 1. So the mean free path length is 1 over that, 1 over rho to the d-minus 1. So what you need to do in order to have any chance of seeing a limiting process is you need to measure your time and your space units on the scale of the mean free path length. So that's what I'm doing here. So I'm introducing new coordinates, macroscopic coordinates that measure things are measured in units of the mean free path length. And we now define a macroscopic flow, and that's again, is just the standard billiard flow, the standard Hamiltonian flow of your system in those macroscopic units. And the question now is, if we start with some initial particle density F, we propagate it with respect to the laws of classical motion to some density at time t. Does that converge as rho tends to 0 to some limit? Of course, we only expect weak convergence. And indeed, what Lorentz suggested in his paper, following the heuristic arguments of Boltzmann, is that you should see a transport equation for the limiting dynamics of this form, so that the limiting dynamics is no longer deterministic. It will be governed by a random process. And this is the linear Boltzmann equation. It's linear in F. It's linear because we look at the one-particle dynamics. And so what you see here is this is the standard free propagation. And on the right-hand side, you have a collision term that tells you that uniformly in time, the velocity of a particle will jump from v prime to v with a transition probability that's given by the differential scattering cross-section. The remarkable thing about this is that the particle, or the limiting process, really only sees a single scatterer, right? So when you hit something, it just sees one scatterer, and that's reflected in the fact that the right-hand side here has the single scatterer cross-section built in. This equation has many applications: a neutron transport, radiative transfer, and even I've seen a paper where people model water waves near the polar region where you have many little ice planks. So very topical. Of course, we get more and more small ice planks. So it's whenever you have wave scattering, for instance, or particle scattering with small scatterers, then this equation appears to be a good model. So the main question is now, what kind of random flight processes can we observe in this Boltzmann-Grad limit for various scatterer configurations? And what are the associated kinetic transport equations? Do we perhaps see other equations than the linear Boltzmann equation coming up in such a limit? And when I talk about a random flight process, what I mean is it's a stochastic process where you fly along a straight line for a random time, then you change direction, and you fly again for a random time. That may depend on all the previous data, but the key point is it's not Brownian motion where you sort of change direction constantly, but you really have a flight path, then you change direction, and then you fly again. And we expect this, of course, because this is how we rescaled our length units. We measure distances and time on the scale of the mean free path lengths, right? So the mean flight time is a constant in the scaling that we've chosen. It's just some subset, P, just the point set P. So far, I've only assumed that it has uniform density. That's all for so far.
Flight of some distance, and then you can change your angle by some random angle and put that model.
No, mine is completely deterministic. The only randomness in my system is in the initial condition. Nothing else is random. And so let me just tell you what are the key quantities we now need to keep track of in order to answer those two questions. Well, the first one is, of course, the initial data. So we start at some point Q naught, and we start with some initial velocity V naught. And as I said, these are taken to be random. And then tau 1 will denote the first hitting time. Vn will denote the velocity after the nth collision, and tau n plus 1 will be the free path length after the nth collision, and then I combine this to a vector of length Tn and velocity Vn minus 1, which just simply describes the vector or the leg of your journey. And I call this a travel itinerary, yeah? So it describes exactly your complete trajectory up to the nth collision. And once you have your itinerary, then you, of course, can reconstruct the process by just flowing with unit speed along those segments. Patience, Dima. The Sn is exactly this vector, that's S1. This is S2, so it's not the sum, it's just each individual. Yeah? And remember, the mean free path goes like 1 over rho to the d minus 1, so it grows in those microscopic units, and then, that's why we need to rescale. So let me just give you a graphic illustration. So these are the kind of sets we want to look at. So on the left, you have a random set. So this is simply some points thrown at random, say a Poisson process that we freeze. Or on the right-hand side there we have a lattice, Z2 in this case, but we can take other lattices, other periodic point set. That's just for the purpose of illustration. Here the scattering radius is 1/4, the mean free path length therefore is 2, and now we shrink, right? So we make our scatterer smaller, and we want to understand, you can now imagine, have a particle flying around here. What will happen? The mean free path length will grow, and so eventually we only see a straight line. We need to rescale. And that's the point of introducing these macroscopic quantities, as I described earlier. So now with the capital letters, we have the analogous macroscopic quantities, the psi, j's correspond to free path lengths rescaled. So tau 1 will grow, like grow 1 over rho to the d minus 1. So if I multiply it, this will become a quantity where we can hope to have a limit. And so the SNs are now the macroscopically scaled length of our journey. There should be a little SN here. And the mean free path length is now a constant, okay? That's what we want in those units. And let me just reiterate, these are all deterministic functions. Nothing's random here. They're all functions of the initial condition only. And so in this picture, in these macroscopic coordinates, what we now do is we zoom out exactly by the mean free path length. So, and what you see then as we scale out, you can now see that by zooming out, we have increased the density, so we are moving now with a constant mean free path length as we zoom out, yeah? Does that make sense? So the mean free path length here is now fixed in all those pictures. So, what can we prove? So for P that will satisfy certain conditions, we can prove that indeed the classical dynamics for this sequence of dynamical systems, rescaled in the way I've showed you, converges to a limiting random flight process. So in order to tell you how we define a random flight process, let me just denote by nt the number of collisions within time t. And then you see Tn now is the total travel times up to the nth collision. And we can now produce a continuous time process in our phase space, in our unit tangent bundle of Rd, by simply moving with speed 1 along those legs of our path. And this is just what I've written down here. So you start at q0, then you travel through all those times until you are after collision nt, and then you still flow with finite time. And the velocity is, of course, vnt. That's the velocity after the nth collision. Now, this defines a random flight process because if we choose q0 and v0 to be random with respect to some initial probability measure on our phase space. So I fix that. That describes my initial particle cloud, if you wish. Yeah? So I fix some initial probability measure for our particle trajectories, and then this defines a random flight process, which is as far away from random as you can imagine, because the only randomness is in the initial condition. So it's completely deterministic up to the initial condition. However, PAC, oh, I'm sorry, it's absolutely continuous. So we want our initial probability measure to be absolutely continuous. Otherwise, it won't work. Yeah. And so what this theorem then says is that indeed, if we have a sufficiently nice initial probability measure, then there is a limiting random flight process so that our Lorentz process here converges in distribution to this limiting flight process. And this limiting flight process will now be a proper random process. And I'll explain a little bit more of how it will look like. So in fact, what you can show is that it's a Markovian process on the appropriate extended phase space. No, the XE here are functions of the initial, right? So they're completely determined by the initial data. Now they become random, of course, if you choose your initial data to be random, but they are, of course, highly correlated because they only really depend on the initial data. So the answer to your question was yes, they are random, but only if you choose. So I'd like to think of functions of the initial data, and then you can define them in this way. Is that clear for everyone? It'll become clearer when I now tell you what the limiting process looks like. So in order to prove this theorem, as you've seen, is once we understand whether or not our path segments converge in distribution to a limit, then we can recover the random flight process because we just move with unit speed along those path segments. So what we really need to show is to simply consider the sequence of free path lengths and velocities and show that this sequence, which again is a random sequence because it depends on the random initial data, converges in distribution to a limit. Yeah, once we have shown this, then up to some technical details, we get also convergence of the random flight process. Everyone happy with that? And in order to prove this convergence, you only need to look at finitely many, so you truncate the sequence up to the first n collisions, and you want to then prove that this vector of the first n segments converges to a random vector here, and you want to do this for any n. Okay? So there are three main steps that you need to complete to do this. So first of all, we need to do a rescaling step. As you've seen, there are three length scales that are important here. The first length scale is microscopic, that's the scatterer size, that's rho. The second length scale is the mean separation between our scatterers, which is of the order 1. So if you think of the lattice picture, the lattice spacing is 1. And then we have the third length scale, which is the mean free path length, which goes to infinity. So two of those length scales are important, and they'll survive the limit, but we need to rescale them. So clearly the scatterer shrinks to 0, but as you've seen in the Boltzmann equation, we see the scattering process. So we need to capture that length scale. And we also will see our random flight process. So we need to capture the mean free path, and that's why we've rescaled that. We will no longer see a lattice in the limit, or the lattice we started off. And we also won't see the particular point set we started off because we zoom out, and that disappears into a continuum. So that's the first rescaling step. And then we need to understand what's the probability that if you start from one scatterer that you will hit another scatterer at a certain time. And you also need to see where you hit that scatterer. The second step then is that this sequence here will be not necessarily a Markov chain. And that's bad because what we would like, of course, is to iterate this argument. So if in the limiting, in the limit we don't get a Markov process, then we will find it very difficult to iterate our argument. So what we do here, and this is the key step in this work, is to extend the state space of our limiting process so that it becomes Markovian. And then finally, we perform exactly this induction argument on the number, on the collision. So we assume we have proved convergence for the first n collision. Can we then find the probability for the n plus first collision? So that's the plan. So let me explain first of all the rescaling step. So we want to rotate RD so that the particle shoots in the horizontal direction, the first coordinate axis direction. You have to think that we now want to think in terms of the particle itself. So we are the particle, and we want to align our coordinate axis in our flight direction, okay? And then the next step is that we want to apply a linear transformation that takes care of the direction I'm flying, because I'm flying for very long, remember? So I want to rescale that very long direction by multiplying everything by rho to the d minus 1. And the direction perpendicular to my travel is how I see the scatter, which is tiny, so I want to blow that up. So I just apply this diagonal matrix, and the beauty of it is, of course, it has determinant 1. Right? So that's what that's a critical observation. Of course, it has determinant 1 because the calculation of working out the free path lengths exactly uses a volume argument. So it's not an accident, it has determinant 1, but I just want to highlight it because what's going to happen now is that we are in a position to apply homogeneous dynamics, right? We rotate and we stretch. That's what we love doing. So that's exactly why you can now apply these things. So here's just a cartoon of what we want to do. So here's the scatterer we are currently at. And so assume we've come in with a certain velocity. So the particle came from here. It's just been reflected, and now it has velocity Vn. And this is the particle trajectory. And what we want to describe here is when will the particle hit the next scatterer. Here you see the radius of the scatterer, or the diameter of the scatterer. Yn is the position of the nth scatterer. And this is the travel time. So this would be exactly psi n plus 1, but rescaled, of course, because this is the macroscopic unit and this is a microscopic picture. So now how can we characterize whether or not we hit the next scatterer exactly at this distance? Well, you can characterize it by, well, either saying, well, this ray here shouldn't intersect any other scatterer, because obviously if it intersects any other scatterer, then I would have hit that scatterer. Or equivalently, if no point from our point set P lies in this blue exclusion zone here. Is that clear to everyone? Yeah, so, so having no point in this exclusion zone is equivalent to the fact that not intersecting a scatterer. Right. So now when we apply our linear transformation, what happens is, well, first we rotate and we get a picture like that. And then we, before I do this, the critical variables here that we need to keep track of is actually the so-called exit parameter, which I call Bn minus. So this is the exit point projected onto the hyperplane perpendicular to my exit direction. Yeah, so now I'm flying to the right because I've just rotated everything. And this is the impact parameter. And you see we still have our rho in here because the scatterers have size rho. So once I now apply my stretching matrix, my linear matrix, I get a picture like this, where the rows have disappeared completely. There's no row here anymore, and there's no row here anymore, and that was the whole point of the exercise. So now, what you see as well is that in the direction of travel, my spheres become very thin ellipses. So actually, you can think of them as just disks with zero. So basically, the ellipses become flat disks. And the beauty of it is that as you take rho to 0, rho will then have completely disappeared from this picture. No rho anymore. However, of course, the price that we've paid is that our point set P now has been messed about with, yeah? So it has been translated so that the scatterer I'm currently at is the origin, and then we have applied our linear transformation, we have rotated it, and we've stretched it. So rather than thinking now of a random trajectory, we are thinking of a trajectory that's just moving to the right with unit speed, but our point set has changed. Our point set has now become a random point set. Why is it a random point set? Well, remember, v is random here, right? V is the velocity we're traveling in, and v is random. Also, y is random, because which scatterer we hit after n collisions is also a random variable, because the initial data is random. So y and v are random. So we now have a random point set, and we would like to understand whether this random point set intersects my blue cylinder that's no longer rho dependent. And if it doesn't intersect it, then we know that we have satisfied our condition. We also need to condition it, our random point set, so that there is a point. Let me just show you this picture again. we need to condition it so that there is a lattice point here, not a lattice point, a point from P here and a point from P there. And no point inside, okay? So this now allows us to simply think of this question as a question in terms of point processes. A random point set is a point process, and we want to characterize a free flight as the probability that a certain random point process has a point, 2 points on the boundary at given positions and no point inside. So that's the main thing. Of course, the problem is pretty difficult for general point sets, and what you don't want is that you get wildly different distributions for every scatterer that you're looking at, for every y, right? Because then we would just lose control of everything and we couldn't actually prove anything. So we need to assume that somehow the limit point process that we get for each scatterer are nice in some sense. And in order to do this, we keep track of the limits by assigning a certain mark to each scatterer in our point set y. And we want that the space of marks, which I call here sigma, capital sigma, is some nice compact metric space that carries a nice probability measure. So of course, what you could do is you could just take your point set P, it's a countable set, you so could just give every point in your point set P a different mark, right? But that wouldn't be a very nice metric, compact metric space. So we need this. So I'm now coming to the assumptions on the point set that Dima asked. And this is really, I think, where the main, I guess, thought has gone into setting up these conditions and make the convergence proof work under these conditions. So first of all, so we say that P is admissible if we have such a compact metric space, sigma, and a map, which we call the marking, that assigns every point a mark in that space of marks. So we now extend our RD by the space of marks in this way and define now a so-called marked point set. Okay, that's all. So I'll give you a few examples in a second to illustrate what's happening here. And then the first assumption is that, so remember what I started off with is saying if we count the points in my point set P that fall into a large domain, it should be asymptotic to the volume of that domain. That was an initial assumption. We now need to extend that to also make sure that the marks are uniformly distributed with respect to a suitable measure on our space of marks. So I call this M. So we have our mark space, sigma. We want to find a probability measure M on that mark space, so that when I count my marked points now, that the frequency of finding a mark in my big domain converges or is uniformly distributed with respect to M. So that's the first assumption. And the second assumption is, as you've seen, we need to show that this randomly rotated and stretched point set converges to something. Otherwise, we wouldn't get to limit, because remember, that is characterizing the probability that there's no point in my blue cylinder. So I want to have that as a limiting distribution. And I now need to extend this convergence by assuming that also my marked point set or my marked point process converges to a limit. Yeah? So these are essentially the two main assumptions that we have on our point set P. So A, some asymptotic density, and B, spherical average should exist. Question?
Random walk with random instruments and the random angle with respect to the spherical measure?
Because at the moment we are so at the moment so you're right, of course, that if I just look at the initial question of shooting a point and hitting the first scatterer, that looks almost like the same assumption. But what we'll show is that this is actually the only thing we needed, because part of the proof is now to iterate this argument, right? Is not yet guaranteed, right? So this, you're absolutely right. I mean, this assumption would immediately imply that we have the distribution for the first flight time, but not for the second and not for the third and so on. So let me give you, first of all, some examples of admissible P. So the first one is we throw down a Poisson point process and we freeze it, okay? So you're not allowed to change your point process afterwards. So you just look at a fixed realization, and then we can show that it satisfies the assumption, and your mark space here is trivial. So we can give every point the same mark, 1, let's say. We don't need this. We don't need a more complicated mark space to satisfy our assumptions. Yeah? So just to recap, what was really important here is that it's not that you give me a P and a mark space, you just give me a P and I have to find the right sigma and the right M so that these conditions are satisfied. So for a Poisson, realization of a Poisson process, we can just choose the trivial mark space, and the proof that it actually satisfies those assumptions is non-trivial. Because remember, we need to show that for almost surely for a realization of a Poisson process, the spherical average converges. That's a non-trivial statement. It would be trivial if you would just do the convergence in distribution, because the Poisson measure is invariant under linear transformations with determinant 1. No, they just proved it for this realization. And they proved the complete conclusion. And so if you like, we've prepared the part in their argument that satisfies our assumption. So we actually follow that part of the argument, but they had to do more because they also had to iterate this process, which of course is simpler if you have a Poisson point set, but it's still very difficult. So we're not making the point here that we are proving anything new. We just say that the framework we have here applies to the Poisson point process. And what is more is that they could only do it for hard spheres. We can do it for general potentials, and we get it for free, if you like, through our technique. I'll come to that. So the point, I'll come to that in a few slides. So let's just concentrate now on the assumptions that they're satisfied. I just wanted to illustrate that. So another classic model that was studied previously was the periodic point set. And again here, you also only need to put the trivial marking. And the second assumption of spherical average follows from the spherical equidistribution on the space of lattices, which follows in turn from the mixing property of the diagonal flow on the space of lattices. So this is also well understood. And there was a long history of investigations of this problem. By D rho, yeah, exactly. That's what I mean by spherical average. And you know this better than anyone, that it becomes uniformly distributed. And as I said, before our work, so this again is how we proved the convergence of the Lorentz process in the periodic setting in the limit using the spherical average. And again, we didn't need a mark. So the point of this new work here is really that for more complicated scatterer configurations, you actually do need this marking, and that's, I guess, the main or the main creative point of our work. And here's the first example. So you don't look at a lattice, but you look at a general periodic point set, where you start with a Euclidean lattice, L, and you look at its translates, M translates of it, take 2 translates. And in this case, the mark space that you choose is by giving each translate a different mark. Yeah, so you label them from 1 to M. And then the assumptions, the spherical equidistribution assumption, can be established by using spherical equidistribution on SLDZ semidirect product kth power of ZD. Sorry, I should read it the other way around. SLDR semidirect product RD to the kth power modulo the arithmetic subgroup. And in order to prove this spherical equidistribution result, you really need Ratner's theorem, because you now have a spherical average that's significantly lower dimensional and doesn't project, the sphere doesn't project onto the full horosphere, but only on a smaller horosphere. So that's one new example. And then, which said, yeah, the end is wrong here. Admissible, so admissible follows from spherical equidistribution, which follows from Ratner's theorem. It's correct, yeah. But that's the meaning of it. And the fourth example, which we're particularly happy about, is sets like a Penrose tiling. You take your favorite Penrose tiling and you put a scatterer on each of the vertices. That defines you a Lorentz gas. And in this case, also our assumptions are satisfied. In fact, for all sets that can be constructed as a cut and project set. So cut and project sets, or Euclidean cut and project sets, as I call them here, are sets where you start with a high dimensional lattice. You take a slab of your lattice points and you project them down onto your RD, okay? And for such sets, the space of marks will be, so now you have a set in RD that comes from a higher dimensional space, and your mark will be the height of the original lattice point in the higher dimensional space. Yeah, so you take your high dimensional lattice, you take a slab, and you project down. By the amount you have to project down, that quantity will be your marking. Yeah, because in these Euclidean cut and project sets, the slab has a compact cross-section. You can, of course, do wild cross-section. I'm not going into these details here, but the point is that sigma will be exactly the cross-section of your slab, yeah, and then it'll be compact. Does that make sense? Okay. So, and again, the proof of these assumptions uses equidistribution of lower dimensional spheres in the space of lattices. And again, it shouldn't be and, but which follows from Ratner's theorem. Good? So these are the 4 examples. These 2 are new, and the previous 2 are old, but also fit into our general framework. Okay, so now this is really the main theorem that we prove and which we can apply the inductive argument. And the key observation now is that the original flight process, where I only keep track of the flight length and the direction, will in general not be Markovian. However, if we keep track of the marking of the scatterer that I've just visited, and also the impact parameter, so where I hit the scatterer, then I can make it Markovian. And this is what this theorem is saying. So I'm now looking not only at the free path lengths after the jth collision, I'm also looking at the marking of the jth scatterer and the velocity afterwards. If I look at those quantities, then this will converge in distribution to a second order Markov process.
Are you doing this process on some random surface above with some random height?
Yes, you could think of it that way. So if you really want to think of the cut and project set, you could think of a process where it is actually a higher dimensional process. Yeah, that's one way of thinking about that. We don't think about it this way because we like to think of the marking also as an abstract variable, because there can be other way the construction is not so geometric. But that's exactly right. So for the quasi-crystals, that's, I think, a good way of thinking about this. So second order means that you have memory too. So is that okay as an answer? Yeah. We could take a larger space, but then it would be harder to write down. And it's a good point because, of course, on the larger space, your transition probabilities will be then quite singular as well. Okay, so this is the main theorem. So I need these three. So the main point is I need to add the color to it. And in fact, that's why I mentioned the impact parameters. You can also construct another process where you keep track of the impact parameters, and then it will be a first order process in general. But we want to think about velocities here. The impact parameters are determined by the velocities and vice versa. Okay, so now the transition probability of our Markov process is given by, so this is the initial density, and then the transition probability between the j's and the j plus first step is given by this, and here you see that it has memory too. Yeah, so that the fact that our transition probability just doesn't depend on j minus 1 and the color j at the j minus 1 collision, but also at the velocity at the previous collision, means it's second order. And this is the complete variable dependence. In particular, you see here, we don't actually care about the flight time in the previous scattering. That's not relevant. And I guess that's an important thing here. Okay. So once you have this, then as I said, you can, you also get convergence modulo some technical arguments of your random flight process. And once you have the random flight process, you also understand the dynamics of an initial particle density. The dynamics of the initial particle density is simply defined by the last point of your random flight process. And so you get this as a corollary. If you start with an initial velocity, you get convergence to a limiting family of operators that describe your density at time t. And again, the observation is here that this family of operators LT doesn't necessarily form a semigroup. So in order to get a semigroup, you need to extend your state space and look exactly at the same state space that made our previous process Markovian. So your density should also record the marking and the flight time to the next collision. If you do that, then LT will form a semigroup, and the corresponding density, if we assume that our initial density is sufficiently smooth, will satisfy a linear transport equation, which looks like the linear Boltzmann equation, but it isn't. It's a generalization of the linear Boltzmann equation. So that answers the second question I have. Really, the limiting process that you get, as we've seen, depends on P, right? Because P determines, for example, the mark space that we need to pick. And it therefore also determines the transport equation that corresponds to our random flight process. Now, in the case when we have a Poisson scatterer configuration or other scatterer configuration whose limiting process is Poissonian, then you can show that this transition probability here is actually e to the minus xi times the differential cross-section. And you can then show that this equation, through a simple ansatz, reduces to the linear Boltzmann equation. So this is really a generalization of it. And as we've seen in the Poisson case, we don't need marks. In the case of a lattice, you also don't need marks, but you have a non-trivial collision kernel here. So in that case, you don't reduce to the linear Boltzmann equation. So the fact that our mark space is trivial doesn't imply that we get a linear Boltzmann equation. But if we need a non-trivial mark on our initial point set, it means we get an even more complicated linear Boltzmann equation. Okay, so there are a number of open problems that are on my to-do list. The first one is all the examples that we had start with a point set P, you apply the spherical average, and you get a limiting random point process that's SL2R invariant. It would be very interesting to see whether there are any non-SL2R invariant processes that arise naturally in this limit. And you also see that this connects nicely with the work of Eskin and Mirzakani and Mohammadi, where they looked at spherical averages in the modular space of flat surfaces. And again there, they couldn't establish spherical convergence, but only on an additional average over rho, if you like. So this question somehow connects with this set of problems. It's of course much more general because we talk about just about general point sets P, not those that come from saddle connections in the translation surface. A real big challenge is to put external force fields, so now your trajectories will be curved. And then, of course, we have no clue what to do because the linear rescaling doesn't work. So in this case, in the case of lattices, for instance, this will be a very difficult problem. And then you ask about the long time limit. Will it converge to diffusion? So in the case of Poisson, we know that there is a there's a convergence to Brownian motion under diffusive scaling. We know that for lattice configuration, we have convergence to Brownian motion under super diffusive scaling with a T log T mean square displacement. And then what I'm working on currently as well is the quantum analog of these problems, which is also open. So thank you very much.